All right, so in the last section we were getting an introduction to binomial random variables, and today we're going to look at how to calculate the mean and standard deviation of a binomial random variable. So as it says, if x is a binomial random variable with parameters n and p, in other words, like we said, x is represented by the binomial distribution n and p are our number of trials and our probability of success, then the mean of that random variable, mu, is just equal to n times p. That's your expected amount. And the standard deviation is sigma is equal to the square root of n times p times q. And just remember that q is really just equal to 1 minus p. Also, something I want to point out in your book is sometimes you will see the following notation. As opposed to this, which is more traditionally written, sometimes they will write it BIN. Still stands for binomial, means the exact same thing. All right, so let's use those formulas to look at a couple problems. So the first one, I'm giving you no context. Just suppose that x is a random variable that can be represented by a binomial distribution where 5 is the number of trials, n, and 0.3 is the probability of success, p. First thing we want to do is we want to find the mean and the standard deviation of x. Well, according to the formulas we just saw, mean, or mu, is equal to n times p. So in this case, that would just be 5 times 0.3, which is 1.5. And then standard deviation is the square root of n times p times q. So that's going to be the square root of 5 times 0.3 times q is the probability of failure, in this case 1 minus 0.3, or 0.7. Multiply that out, you get approximately 1.02 for your standard deviation. All right, the next thing we're asked to do is to graph the distribution using a histogram. What they're asking us to do is to plot x, the outcome, against p of x, the probability of that outcome. So this really has nothing to do with mean or standard deviation. This is going back to what we were doing in the previous section. So what we need to do is use the formula for binomial probability, which is that p of x is equal to, not p of x, let me change that. The probability that x equals some specific outcome r, number of successes, is n choose r times p to the r times q to the n minus r. So I'm going to make a little table here for us. We're going to compare x to p of x. Now, we need to consider all the possible outcomes. In this binomial distribution, n is 5. In other words, we have 5 trials occurring. Doesn't matter what we're looking at. We could be shooting 5 baskets. We could be randomly selecting 5 people and figuring out whether they're left-handed or right-handed, or we could be, for instance, any sort of thing. But we've got five trials. And so we got to consider all the possible outcomes. The possible outcomes is the number of possible successes. Well, if you have 5 trials, there's actually 6 possible outcomes. You could have 0 successes, 1, 2, 3, 4, or 5 total successes. So we need to calculate the probability of each of these outcomes. So first I want to calculate the probability of 0. Well, according to the formula, that would be 5 choose 0 times 0.3, which is our probability of success, to the 0 times 0.7 to the 5th. And you work that out and you get approximately 0.168. If you want to know the probability of one success, that would be 5 choose 1 times 0.3 to the 1 times 0.7 to the 4th, which is 0.360. I won't bore you with all of these. You can calculate them on your own if you're that interested. The rest of them end up being 0.3087. I recognize that's not to 3 significant digits. Shame on me. 0.1323, 0.0285, and 0.00243. All right. Now we've got our outcomes listed and our probabilities of each of those outcomes. So we now want to draw in our histogram. Along the x-axis, we're going to label our possible outcomes for our random variable, which is 0, 1, 2, 3, 4, 5. Almost running out of room there. And along the y-axis, our probabilities. Now our highest probability is 0.360. So we don't need to go all the way up to 1. Let's just go up to 0.4, for instance. So I'm going by 0.1, or by tenths. And then I'm just going to do my best to estimate these. Probability of 0 is 0.168. So it's roughly right there. Probability of one success is 0.360. Getting a little bit off, but that'll do. Probability of two successes is 0.3087. Approximately right there. 3 successes is 0.1323. Four successes is 0.0285. We're getting pretty low. And 5 is 0.00243. Almost impossible in my situation to draw accurately. All right, and there's our binomial distribution graphed using histogram. So last thing we're asked to do is to comment on the shape of the distribution. In other words, is it bell-shaped? Is it positively skewed? Or my computer just went blank. All right, I'm back. Just to fill you in, my computer didn't go blank. It was actually my projector on my smartboard, which I'm using right now, went blank. Just a little comedy of errors there for you. I'm sure you enjoyed the joke. Yeah. Anyway, back to the shape of the distribution. So we want to check whether it's bell-shaped, positively skewed, or negatively skewed. As we all know by now, imagine little Sally climbing up the ladder and sliding down the slide. And that means, since she would be heading in the positive x direction, that this is positively skewed. It's clearly not bell-shaped because the mode, the highest bar, is not in the center. All right, that's it for that one. Okay, last example to look at. So let's consider this scenario, and let me tell you what, I put some pretty serious time into conducting some action research here on this. So what I found is that only 38% of the chocolate chip cookies that I, Mr. Evans, bake are actually humanly digestible. If I bake a batch of 12 cookies, and x, the random variable x, represents the number of digestible cookies in that batch, find the mean and standard deviation of the x distribution. All right, first let's describe this as a binomial distribution. Well, is it binomial? Well, we've got, it's certainly discrete because we have two possible outcomes. Each cookie is either digestible or indigestible, not digestible. And each trial is independent because whether or not one cookie is digestible does not impact whether or not another one is, assuming that I created them randomly. I baked them randomly. So we've got the random variable x here being represented by a binomial distribution, wherein the number of trials is 12, and p, the probability of success, that it is in fact digestible, is 0.38. All we're interested in is the mean and standard deviation. This is pretty straightforward. The mean, as we mentioned earlier, is just n times p. So in this case, 12 times 0.38, which is 4.56. In other words, you'd expect about 4.5 of my cookies to be digestible. And the standard deviation is the square root of n, 12, times p, 0.38, times q, which is just 1 minus 0.38, or 0.62. And that gives us a standard deviation of approximately 1.68. And that, my friends, is all she wrote. Have a nice day.